All right, what's up, everybody? Glad you are back, David. We had a black screen day on Monday, so it's good to see somebody joining us. Yay! Okay, welcome everybody, not just David. I'm happy to have all of you here. So the plan for today is to start talking about Chapter 7, which is dealing with confidence intervals. So good thing is we've kind of worked with these before from a simulation point of view, doing bootstrapping. And now we're going to talk about more classical methods for confidence intervals. And we'll be using kind of formulas, built-in formulas in R in some sense to do that. So we won't be creating bootstrap distributions, but we're still doing the same thing in the end, which is trying to come up with an interval estimate for some population parameter whose value we don't know. So before we get started, I just want to mention one thing, and that is there was a typo in the homework that somebody pointed out, and thanks for pointing that out. And that is in regards to, so this is homework 8, by the way, and this was question number 2. And in question number 2, the values for X should go from 0 up to 1, and the values for Y should only go from 0 to 1. And my initial values had things like 14 and 12. Someone caught that, and that was good. That was just a formatting error in the PDF. So that should have been 1/4 and 1/2 and stuff like that. So if you've already done this problem with the bad values, okay, fine. Just let me know that. You don't have to go back and redo it. But if you got stuck on this problem because of those values, please just make sure this has been updated in Canvas. Just make sure you're using the most updated PDF in Canvas. So again, this was an error in question 2, and that was these values over here were not formatted correctly in the first one. The 1/4 was looking like 14, so I changed that back. Any questions about that? Sorry about that. Okay, so yeah, so that homework assignment, like I said, the first 3 problems are on Chapter 6. So those you should definitely, if you haven't gotten through them, get through them. And then the rest of the assignment is going to be on things that we're talking about today. So before we get started, are there any questions? I am going to just chat 2 files over to you in case you don't have these. One of them is the worksheet that we'll be working on today, which is worksheet 14. Here it is. I think I can do this. And if you want to play along, we're going to do a little kind of thought experiment. If anybody here is fan of the artist formerly known as Prince, we'll be taking a look at Raspberry-Beret. So there is a file on Canvas called Raspberry-Beret.R. I think I can send an R file, yes, as well. So that's not an R markdown file. That's just a straight up R file. Okay, so is there a question?
That worksheet's not on Zoom?
Which one?
Or not on Zoom, on Canvas, the 14.
It's not?
I just thought you were sharing it here. You can ignore me.
So I just chatted both 2 files in, and worksheet 14 should be up in Canvas as well in module 12, week 12.
I see it. Yeah, I thought you were sharing it because it wasn't there.
Yeah.
Thank you.
Yep. Okay. So I'm going to be working a little bit in R and a little bit with the PDF today. So sorry if I jump around between those 2. And let's hope the technology behaves today. So just want to start by talking about some of the things that came up on your reading quiz for today. So the idea here is, whoa, that's not helpful. Okay. So the idea with a confidence interval is we're trying to approximate a population parameter without making a claim about it. So we're not doing a statistical test, and we're not claiming like, hey, is the average sea temperature bigger than this, right? We're just trying to say like, what is the average sea temperature, sea surface temperature, something like this. So the idea here is now we're going to pick one sample. And in the past, what we did is we used that sample to create bootstrap distribution. And we're going to take a different approach in this chapter. So in this chapter, we're going to use a more theoretical approach that's basically using the central limit theorem. So we're going to kind of get an approximation for this sampling distribution. And then based on that sampling distribution, we can use the sampling distribution similar to how we use the bootstrap distribution. So let's just consider here, rather than take on something really complicated like the temperature of the ocean, let's just say we have a population, and our population is going to be all of the lyrics of Prince's song Raspberry-Beret. You guys familiar with that? You can Google it. Yeah, old song back from the 80s. And I just picked this because this is a case where we actually know what the population is, so we can compare our predictions with the population. Generally speaking, we don't have all of the data. So in this case, I know every word that is in the song, so I do have the population. Generally speaking, we usually don't have the population. So if we take all of the lyrics of Prince's song, and we're going to try and come up with a confidence interval. So let's say we didn't know the population, but we wanted to come up with an estimate for what is the mean length of a word. And again, this is a case where we actually can calculate that, but just kind of pretend that we didn't know what that was. Then what I can do is I can pick a random sample of words from the song. And so here, length, what we're measuring the length is like the number of letters. And so if we all pick a sample and we calculate the mean of our sample, we're going to get different things, right? Because we're going to pick different words in our sample. So the values of the X bars will be different for each of us, right? This is what happens with polling, right? Different organizations come up with different predictions because they've polled different people. So the X bars are going to vary from sample to sample. The underlying population mean is not random, right? This is just, it's unknown. So there's a difference between saying something is random versus something is unknown. So this guy over here, the X bars, these are random because they depend on sampling. The mu, not random. This is a fixed value. We just often don't know it. But just because we don't know what it is doesn't mean that it's going to be different for different people. So the value that we're trying to approximate in the end is going to be the same for all of us. So the population mean is not random, but the samples that we get to make a prediction are. And then, so this was worked through in the video, so I won't do it again here. But this is using really this fact that 95% of values in a normal distribution, right? So remember, we had this kind of rule of thumb that was 68% was in 1, 95% was in 2, 99.7% was in 3. And so now the distribution that we're looking at is no longer X, where we're thinking about the distribution of sample means. So we're dealing with a sampling distribution. So in this case, our standard deviation for a sampling distribution, we would just replace that with the standard error in this case, because the standard error is the standard deviation of the sampling distribution. And here our values are no longer like individuals within the population, but we're thinking about the sampling distribution is a collection of a bunch of sample means, right? So now what we're saying is that out of all of the sample means that we might have in our sampling distribution, 95% of those sample means are going to be within about 2 standard errors of the center. And to be more precise, it's actually 1.96. Okay, so we can make that a more precise rule. So this tells us like where we should expect most of our sample means to be, but we're not trying to make predictions about where our sample means are going to be. So what we're going to do with this sampling distribution we want to predict the value of mu. So we can use this rule to come up with a sort of interval like this, which is exactly what we've got in the previous one. And yeah, so this is exactly saying that, 95% of all of the sample means are going to be within about 2 standard errors of the population mean. Okay, so any questions about some of those comments that were on the reading quiz? Okay, so if you want to go ahead and open up that file, that's what I'll be kind of working with. If you want to look at the PDF, you can probably follow along with what I'm doing in R anyway. Oh, let me open up R. That helps if I want to share it. Okay, so I've got RStudio open, and I am working with this file called Raspberry-Beret. So this is it over here. So what I did is I put in all of the lyrics to Raspberry-Beret, and I called that lyrics. So we actually have the population up here. Let me zoom in case this isn't big enough. Okay. So we can think of this as our population, right? Most of the time, we're not going to know what this is. And this command over here calculates the number of characters in each word. So it's going to take yeah, and it's going to convert that to 4. And it's going to take I, and it's going to convert it to 1. It's going to take was and convert it to 3, and so on. So that's going to kind of give us some numbers now. So this, if I run these 2 commands, and then I take a look at, whoops, what I just created. Okay, changed that vector of words to a vector of letters now, right? So it's counting how many letters were in each of those words. And I can see here that, well, how many words we have, like 300, sorry, there are 370 words in the song, apparently. That's what this is telling me. So each word here was converted to a number based on how many letters were in that. Okay, so that's what's going on in these first two lines of code. So now let's pick a sample. So I want to pick a sample here. So let's use the sample command. And what I want to go into is I want to go into the song. So I'm going to go into this thing, population letters. This is what I'm going to pick from. And I'm trying to remember, what does this ask us to do? We're going to pick samples of size 30. So this is saying, go into that vector, pop letters, pick 30 things at random. And won't matter too much what we do here, but we'll just say replace equals false. So we're going to pick 30 different words out of, so that means we can't pick the same word again. I could pick I twice because I appears in the song more than once. So this is going to pick my sample. It's going to, oh, I see the way that I did it over here. So the way that I'm doing it over here is, I guess, first I said, let's pick a sample, and then let's calculate the number of characters. I could have done this in one step, but maybe this way. This is nice because we can view my sample and then see like which words from the song were picked. And then the next line is going to calculate how many letters were in each of those 30 words. So let me run this. And so here's my sample, and right here are my 30 words that were picked at random. That's great. I got raspberry in there. I think that's happened before. Yeah, there's a question, Stephanie.
Yeah, sorry for when I do the view pop.letters, it doesn't come out like a nice like chart like how yours does. It comes out more like it says like name, pop.letters, type, integer, and then value.
Sorry, I think you cut out at the very end there, Stephanie.
Sorry, it's just like in a row, but it doesn't show each value like that. Is that like a setting that I
You
need
mean
to
like it doesn't show each letter? I mean, each word that was picked?
All right. Well, yeah, and I was doing it for the pop letters one.
So yeah, so this one, right, looked like this, and you're getting something different. Is that the idea? Yeah, if you want to hang back, it's not too important for what we're going to do for the rest of the day. So if I definitely want to see what's going on, but we can maybe chat about it at the end of class. I would have to take a look at your code, I think, to see what's going on.
Okay, yeah, that's fine. Thank you.
Okay, so we've got the population up here. Normally, we wouldn't know that, but all we would have would be my sample over here. And then from this sample, I would say, I'll just do it down here. Let's calculate the mean of my sample. So I'm going to calculate the mean of my letters. I get a sample mean of 3.9. And again, if you're all doing this, you're getting something different, right? And that's the whole point of that first question. We're all getting different values of X bar, although the population mean right, is fixed. If we all enter mean pop letters, we all get 3.72, et cetera, but we're probably getting slightly different means. I'm not expecting you to get a mean of like 6, but maybe 3.85, right? Something pretty close to that. Okay, and so let's imagine, right, that I don't know what the population mean is. That's usually the situation that I'm in. But instead, let's calculate, let's at least approximate the standard error for this distribution. So we're told in the problem that the variance is 3.45 letters. And I could verify that. It's 3.46, I guess, if I was being more precise. But I'll use my approximation, which was 3.45. So if I want to approximate the standard error, right, remember what we would do is we would take the standard deviation, or in other words, we can take the variance of the population, divide that by the sample size, which for us was 30, and then we take the square root of that, right? And so in R, square root, we can hit with SQRT. So normally we take like the standard deviation and divide by the square root of 30. I'm just going to take the variance, divide it by 30, and then take the square root, which is the same. And so what I'm trying to do here is go ahead and create a sampling a confidence interval from my sample. So let me just run this stuff over here. And this is telling me the standard error is approximately 3.39. And so if I wanted to calculate sampling distribution, or excuse me, a confidence interval based on this sample, let me switch back to the PDF. And this one is marked up with some solutions. Then, you know, that might look something like this. So, you know, what you get for your sample is going to be different. I could see what my words were. This was based on me getting a sample prior to class of 3.83, right? So that's my sample. So remember how these estimates started. I mean, if I didn't know what the average length of a word was, of all the words were, my best guess would be it's about 3.8 letters, right? But then I want to build in some error because we're all getting slightly different estimates. And so we should account for that variability. And that's what the standard error does. Okay, so remember the standard error is the standard deviation over the sample size. And now I can use this fact that if I go 2 standard errors above and below my sample mean, that has a 95% chance of containing the population mean. So what I did in this calculation was I took the sample mean, I went about 2 standard errors below that sample mean to get the lower cutoff for my interval. And then I went about 2 standard errors above the sample mean to get my upper cutoff. So for me, that gave me an interval for about 3.2 up to about 4.5 letters. Any questions? And just so I could mark this up. So you might be wondering, like, what we did, at least on my answer key over here, we had like, you guys can see my iPad, right? If I'm writing on that, yeah. So we had a mean of 3.833 plus, or excuse me, we went minus 1.96 times the standard error. That gave me a lower cutoff for this interval, and then we go above by 1.96 standard errors. Okay, and the important thing here is we're not using this. We're not using the population standard deviation. We're using the standard error. So we're finding the standard deviation of the sampling distribution. So for me, that came out to this. And so this is giving us an interval of plausible values for the mean of all of the mean length of all words in the song, which is 3.72, right? So we contained this. I think what was the population? 3.72. Okay, and so normally we don't know what that is, but here we do, so we can kind of just compare our interval to see how we did. For those of you that were going along with this calculation, it's very possible that you did everything correctly and your confidence interval doesn't contain 3.72. That happens sometimes because sometimes you just pick a sample of really short words, right, that have all of the really short words. I got raspberry. That's like a gold mine right there. That's a really long word. Most of the words are like 1 or 2 letters long, right? It's I or or in or so on. So if you're working with that R file, it has a nice little illustration that we can do. Maybe you see it in the corner, but if I go ahead and I run the rest of this code, all that it's going to be doing here is it's picking a different sample 100 times. So I'm just going to generate 100 random samples. And then for each of those random samples, I'm going to calculate the confidence interval. So I'm going to take the mean of my sample and then go 2 standard errors below to get the lower estimate. I'm going to take my sample mean that I got, go 2 standard errors above, and then I'm going to see whether or not that confidence interval actually contains the population mean. That's what's happening in this. So if my interval does contain the population mean, I'm going to create a little graphic that colors that in green, and if it doesn't, it's going to be red. So let me run this. What happened there? Let me try that again. Something weird is happening. Oh, I forgot to run this stuff. Sorry, let me run this stuff up here. Forgot a couple lines of code. Okay, so I'm going to run all of the lines of code from counter all the way down to the end. Okay, that looks way more reasonable. And so what this is looking at over here is a plot of 100 confidence intervals that were run to get this mean. And this vertical bar down the middle is the 3.72. So that's our population mean. Trying to draw, I don't know if you can see this, which is 3.72. And so this is like the first confidence interval, the second one, and we did this 100 times. And out of those 100 times, most of them worked out, and this one didn't. These red ones are ones that didn't work. So this sample had way too many small words in it, this sample had a disproportionate number of big words in it, and so on. So these were all calculated in the same way. They were all based on the original sample that we collected. And if our original sample is biased, then we're going to get a bad result. But most of the time it works. And so here we can see it doesn't have to be this way, but it worked out exactly that 95 out of the 100 samples were a success. And I have 1, 2, 3, 4, 5 ones that didn't work. So this matches what we were saying, right? This captures the population mean 95% of the time. Any question about that? Okay, so that's it for Raspberry-Beret. Hopefully, if you were playing around with that, it was working for you. If it was not working for you, I can happy to take a look at what might have happened in your code. Okay, so just to kind of summarize this process, let me not show you a black screen. In general, if we want to approximate a population mean, and we happen to know what the variance of the population is, then at least for a 95% confidence interval, what we did above is we take our sample mean we have a nice general formula for doing this. And kind of the advantage here compared to like the bootstrapping technique is we don't need technology to do this at all, right? We calculate a sample mean. We could do that with a 4-function calculator. So kind of all of these operations are pretty basic, and that's why this is kind of a more traditional technique. This is how people did things before we had the power of running tons of simulations. Any questions so far? Okay, so the actual calculation of the standard of these confidence intervals, I don't think is too bad. But what I do think is subtly something we want to pay attention to that you might brush off is how do we make sense out of these intervals that we're calculating? How do we interpret them? So I was a little bit lax in how we were doing that. Or I wasn't lax, but I didn't really emphasize this as much when we were first looking at confidence intervals, but I want to make sure we're reading them carefully. So the idea here is, okay, we collect a random sample of words and we construct a 95% confidence interval, and we find out that this 95% confidence interval goes from 2.57 up to 3.9 letters. So the question is, okay, if you were going to interpret what this interval tells us, which of these statements would be good ways of interpreting a confidence interval? So I'm going to open a poll just to see what you guys are thinking about these. So the poll has one question for each of these parts. So there's 5 parts. And the idea is, so in part A, there's a 95% chance that a randomly selected word has between 2.57 and 3.90 letters. So the question is that a correct way that we would read that confidence interval? If it seems reasonable, then tell me that is true. If it doesn't seem reasonable, then tell me that it's false. There is no I'm not sure option here. Got to make up your mind one way or the other. So take a look at each of these statements and see which of them seems reasonable. And you have a homework question that is also pretty similar to this, that gives you several interpretations of confidence intervals. And you got to make sure which of them seem reasonable. So this is good practice for the homework. Okay, so if you are still thinking about this, please take another 10 seconds to wrap up your thought. All right, poll will close in 5, 4, 3, 2. All right, so here's what the class thought about these. So for the first one, 2 people said yes, 4 people said false. So this one is, in fact, not a correct way to interpret that. For someone that said false, do you want to kind of share what you were thinking about that? Why did you think that was not good?
We weren't doing any calculations that any word would be between an interval. It's that the mean
That's right.
would be in that interval.
Yep, you got it. That's right. Good. The idea here is we're not trying to make a prediction for how long one randomly picked word is going to be. Right? For that, we wouldn't use the sampling distribution. So false here, because these confidence intervals are used to estimate a population parameter. So we shouldn't be using this interval to tell us anything about like individuals in the population, but rather if we were to aggregate all of those things together, that's what this interval is telling us. Okay, any questions about that? So for those that thought this might be good, just be careful about what we're using this interval to estimate. So in B, this is now saying there's a 95% chance that the mean length of all words is between 2.57 and 3.90. And so here, people tended to believe that this was true. Some people said that this was false. Maybe we'll have like different degrees of falseness. A was really, really false, right? Because we're not using it to approximate the length of a single word. B is false, not as severely false as A. So this does have the right, it's referring to that, okay, we are trying to approximate the mean length of all words. So that's a good thing there. For someone that said false, do you want to share why you thought that was false? So I would say this is the most subtle one. And the reason why this is false is the uncertainty here is attached to the population mean. So this is kind of going back to some of those true false questions that we started with. The uncertainty here, there's nothing uncertain about the population parameter. It's fixed. It's unknown, right? So there's a difference. We don't know what it is, but it's a fixed value. The uncertainty of this estimate is based on the sampling that we've done, and that is captured by the interval. So we want to make sure, A, that we're using this interval to make estimates about population parameters, and B, when we make that estimate and we attach some uncertainty to that estimate, we should be referring the uncertainty to the interval. Okay, interesting. So in C, everybody thought that one was false. Guess what? This one is true. I fooled you all. And here, the idea is we are using this interval to make an estimate for the mean length of all words. So that part is good. And it's saying that this interval is going to contain it 95% of the time. So the two good things here are this is being used to estimate a population parameter. So that's a check. And the uncertainty here is attached to the interval. Okay, some of the intervals it's going to work, some of them it won't work. That has nothing to do with the population parameter varying. Any questions? Maybe I just stated this a little bit different than how we've been doing it in the past. In the past, we've been doing something like, saying something like, okay, so that's, I think, traditionally how we were doing it earlier in the semester, and that's fine too. Again, this is saying correctly, we're trying to approximate the population parameter. We're also correctly attaching this uncertainty to the estimate. So the only difference between C and what I wrote on the bottom is that the odds, this one says that right away. The other one puts that at the end of the sentence. So it's just the sentence structure, not the meaning of what we're saying is the same in both of those. Let's see, in D, 4 people leaned true here and some said false here. So this is actually a true statement. Okay, the problem is this is not what we use confidence intervals for. Okay, this being, we shouldn't be trying to predict where other samples are likely to be, right? So this has the same error as the first one. So the statement is correct here. This is a correct way really to interpret like a standard error or something like that. But we're not trying to predict if I pick a sample, where is its mean going to be? What we want to do is use that one sample to make a prediction about the population parameter. And then in E, the last one for 5, this was a little bit better. Sorry. So let's think about this. There are really 2 things that we want to be sure we're paying attention to. So the first is we are using this interval to say something about the mean length of all words. And the problem here, this is actually false, and that has the same issue, and that is this uncertainty is being attached to the mean and not to the interval. Sorry about that. Okay, again, that population parameter is just unknown, but it's not a random thing. So when you're going through these, there's certainly like a template that you can stick to, which is like, okay, there's a 95% chance that the interval contains the population parameter, what we wrote down here. But you also want to make sure that if someone else is telling you, here's how I'm interpreting this, that you're listening carefully and making sure that they're interpreting these things in the appropriate way. So this question 4 is saying, well, what are some things to keep in mind? And I would say there's really 2 main things to keep in mind. One is, what are we using these confidence intervals to estimate? Some of these were false because they were using it to estimate the wrong thing. And the second is where you are attaching the uncertainty. And as long as you keep those 2 things in mind, then I think you'll avoid these common misconceptions. Any questions about that? So we just want to be really careful how we use our language and interpreting those. Okay, so want to kind of talk about how we can now tweak a couple of different things in this process. So let's say we want to come up with an estimate for what is the average length of a Komodo dragon, a female Komodo dragon. And for anyone that's not familiar with a Komodo dragon, they're humongous lizards. They're not dragons, they're a lizard, but they're quite large, and they eat mammals. They eat deer, you know, and other things. I think that's why they got the dragon moniker. And so here we've got the sample. I think, what is this? 8, 1, 2, 3, 4, 5, 6, 7, 8. Right? So we have 8 things in our sample. And what we know is that the population standard deviation here is 25 pounds. And we want to construct a 95% confidence interval for the mean weight of all Komodo dragons. So using that previous method that we have, right, we can go kind of 2 standard errors, 1.96 above and below our sample mean. So I don't want to kind of get bogged down in the calculation here, but we could calculate the mean of that sample, adding them up and dividing by 8, and that comes out to 155 pounds. So there's really like two things that we need to know in order to use this formula, right? That is, what is our sample mean and what is the standard error of the sampling distribution? And once we have those two things, then we're good to go. So in this case, we would take our sigma, which is 25, divided by the square root of 8, and that comes out to approximately 8.839. So then what we do is we take this value, right? This gets plugged in for the standard error over here, over here. And this one, we use our mean, and that gets plugged in over here and over here. And the 1.96, that comes from the fact that we have a 95% confidence interval. So this would give us, I'll kind of save you the calculation, of about 138 pounds. This says the length. This is actually the weight of the Komodo dragon. So it would go from 138 up to, this comes out to 172. And that would be our 95% confidence interval. Any questions about that? And so now, if I want to give a 90% confidence interval, so when we decrease that confidence interval from 95 to 90, we have a little bit less confidence in our estimate. These intervals, the odds that your interval is going to contain the population parameter went down by 5%. So that seems kind of bad, but the trade-off is we have less odds of containing the population parameter because we're giving a more narrow estimate. So the good thing about decreasing the confidence interval is you get a more specific estimate. The bad news is you're less sure that it's going to contain the population parameter. So when we change the confidence interval from 95 to 90, the adjustment is not going to be in our sample, and it's not going to be in the standard error. It's going to be in controlling how many standard errors we want to go away. So when we want to make this a little bit less, when we decrease our confidence interval, then we're going to go a little bit less away. And so what I can do to figure out exactly what I need to use that's a normal distribution there, sort of. And so what we saw is if we go kind of 2 below and 2 above, right, that's going to contain 95% in the middle, which means we have 5% missing. No, that means we have 2.5% missing on each side. And now if we change this to 90%, right? Now we've got 90% in the middle, and we would have the 5% below and 5% above. Okay, so what I'm trying to figure out here is how many standard errors should I go if I want to get 90% of the stuff in the middle? So this is what we can use the qnorm function for. Remember, the qnorm function gives us a quantile for a normal distribution. So for this one, we're working with a standardized normal distribution. I'm going to enter 0.95. Okay, and what this function is doing is it's taking, the middle 90% and as well as the tail, which is the bottom 5%. And this formula, this Q norm, is going to tell us what that value is, right? It tells us what is the z-score that cuts off an area of 95% to the left. Okay, so here, for the 90% confidence interval, be careful, right? We're plugging in not 90, but we're plugging in 0.95 because we want to include the middle 90% as well as the stuff in the tail on the left. And this comes out to, if you've got R open, this comes out to 1.645. Okay, any questions about that? Okay, chat. Yeah, let me, someone asked about clarifying that last formula. Let me get a little bit more space. Okay, so here's a normal distribution, and what we're trying to calculate are these values for z that are going to give me 90% in the middle. So when we're doing 95%, right, those values were about 2. And so what R does, if I use this qnorm function in R, so the qnorm function tells me the quantile, right? It's a quantile function. So it's going to tell me what is the value of the random variable so that 95% of the values are less than it, for example. So for the confidence interval, we only want the stuff in the middle. But in order to figure out what this is, we need to take into account, if we're going to use the qnorm function, that we actually want to include all of this area when we plug that in over here. So that's where we want to think about, well, if 90% is in the middle, then we've got 5% in each tail. And so when I use this function, we want to plug in the middle 90% as well as the stuff in the tail. And these guys get special notation. We call them Z alpha over 2. Let me just explain what that comes from. So here we could say the confidence level is 90%. And we say that alpha is telling us how much stuff is not in the middle. And then we divide that by 2. It's not really a percent, but a proportion. That alpha over 2 then takes that and converts it into what stuff is not in the tail. So in this case, we would say that that's z of 0.05. Our alpha was 0.1 in this case. So to find these z alpha over 2, we kind of can use this formula, right? So for us, we subtracted that alpha over 2 in some sense. You could think about it as the area in the right tail. It's the area in the left tail because it's symmetric. So when we use the Q norm function, we want to subtract out that area in the right and calculate what proportion of the rest of the area is to the left. Okay, any questions? So to come back to this example, we would take x bar okay, and so we're just tweaking the fact that this might not always be 1.96. Depends on what the confidence interval is. So for a 90% confidence interval, we would take the 155.5, and we can calculate each of these, right? For the upper one, we're going to go plus. For the bottom one, we go minus 1.645, and the standard error here was 8.839. So here's our answer in B, and we can see that as we, in this case, decrease the confidence interval, our estimate becomes a little bit more specific. It's going to become more narrow. We actually get a more specific estimate, but that estimate is a little bit less likely to be successful. That's the trade-off. So in general, this is the formula that we want to use, where these z alpha over 2s, we've talked about how you can find them. You want to use that Q norm function to figure out what these are. And those depend on the confidence level. And this stuff over here, the z alpha over 2 times the standard error. That's what we call the margin of errors. If you're looking at polling, oftentimes they call it the MO, which is the margin of error. Just be aware that's different than the standard error, right? So the margin of error depends on the standard error. It's the standard error times this Z alpha over 2. So I'll say like the most common confidence level is 95%. 90% is pretty common. 99% is also pretty common. But 95% is the most common one. But don't always use 1.96. Make sure you pay attention to what the confidence level is. Okay, so now we've got all the ingredients that we need. So nobody asked, but doesn't it seem odd that we were constructing confidence intervals for a population that we didn't know the mean, but somehow we knew the standard error, or the standard deviation, right? So up here, when we were doing this Komodo dragon one, we said, okay, we don't know what the mean is, but let's say we know what the standard deviation of the population is. And sometimes you might know that based on past data. More often, you don't know anything about the population. So we don't know what mu is, and we don't know what sigma is. So let's think about how we now can tweak this process to consider situations where both the mean and the standard deviation are unknown. And so what happens is when we do this process, there's going to be 2 changes we're going to need to make. And one is maybe an obvious thing. We're not going to radically change that formula that we've been talking about. Just we're going to use the fact that we can approximate the population standard deviation using the sample standard deviation. But when we do that, although that's an unbiased estimate for sigma, that introduces some additional variability into the estimate. And so when we actually look at a sampling distribution, what happens is the distribution is no longer normal. It is symmetric and it is bell-shaped. It is almost normal, but over here, the distribution actually has more stuff in the tails. So it's a little bit fatter in the tails. And this is what's called a T distribution. And we have all different kinds of T distributions. So for a T distribution, these are described by one parameter, which is the degrees of freedom. So over here, you're looking at a graph of 4 different T distributions with varying degrees of freedom. And so what you can see is once you reach about 30 degrees of freedom, this yellow graph, you're getting something very close to the normal distribution. So I'll just say, as the degrees of freedom head off towards infinity, as it gets large, the T distribution becomes approximately shaped like a normal distribution. Okay, so when we're constructing these confidence intervals for the mean, then rather than use normal distribution to find these cutoff values, okay, we use this command, which is the equivalent of qnorm. And for this quantile t-distribution function, there's going to be two things that we enter. One is the area to the left, and the other is going to be the degrees of freedom. And how do you figure out what the degrees of freedom are? The degrees of freedom depend on your sample size. So the degrees of freedom are going to be one less than how many things you have in your sample.
So it's always just n minus 1?
It's always going to be n minus 1, yes.
Okay.
When we have one sample. Next time we'll have to think about what happens when we're comparing means from two different populations, and that's going to be a little bit more complicated. But when we're working with one sample and trying to predict the mean of one sample, yeah, the degrees of freedom are just going to be how big was my sample minus 1. And in some cases, we have a built-in function in R that's going to do that entire confidence interval for us. But I'll just say this command is going to depend on whether or not we actually have access to the data or whether or not we just have access to summary statistics of the data. So let's kind of take a look at, let's just kind of do one example together. Let's say I want to calculate the mean for the births of all newborns in North Carolina in 2004. And now we have this data set called North Carolina births 2004. And so I'll do this by hand. So there's going to be 3 bits of information that we're going to need to know in order to calculate this. Well, I guess more than 3. So we have these ingredients over here. And I will, I'm going to need to use R to calculate these. So I'm going to just kind of exit out of here. But before I do, I just want to make a note that this is a 99% confidence interval. So that's going to affect what we do for this. Okay. I will actually stay. I'll just write out what the commands would be that I would use here. So the variable for the weight is called weight. So what I might want to do is calculate the mean. I could do mean NC births. I'm going to run out of room. Right, and that would tell me the mean weight of the group, of my sample. So I can calculate the mean and the standard deviation. I'm sorry, I think I'm 1 minute over. So if you need to run, feel free. I'm recording this, but I think we'll just need another minute to finish this. And the N, that's the 1009. I could see that by like hitting view the data set just to see how many observations are in there, for example. And now for this cutoff value, this is the trickiest part of it. For a 99% confidence interval, right, we want to have 99% of this stuff in the middle. And for this example, what would our degrees of freedom be?
$1,008.
Yep.
Yep.
So essentially, our sample is so large here that we might not even see a difference with the normal distribution, but we'll be precise here. So we've got 1008 degrees of freedom, that's right. And we want to find this value over here. So we want to make sure that we include the 99% in the middle, as well as that missing 0.5%. So for this, we're going to use the quantile function for a t-distribution. We want the area to the left to be 99.5, since we want only 0.005 left over to the right. And now we don't enter a mean or a standard deviation, but in here goes the degrees of freedom. And if you want to check that calculation, it's probably, let's see, I'm getting QT. So it comes out to like 2.58. Now, these are all the ingredients that go into that calculation for the cutoffs, right? We need to know what X bar is. We need to know what T alpha over 2 is, standard deviation, and the sample size. Now we've identified all of those things. So now we're just plug those values into the into the formula. So I'll pick up with this next time. I realize now that there probably are going to be some problems on the homework assignment that you won't have a chance to get to. So I'm just going to, rather than cut off the homework assignment, I'm just going to push the due date back to Wednesday of next week. But you certainly could do a number of stuff on confidence intervals. So far, there'll just be a couple that about a difference in two means that I don't think we'll cover until Monday, obviously, since we're out of time. But we'll pick up on Monday, kind of finishing up this problem, actually giving the confidence interval, and then we can compare it to see what this function does as well in R and see whether it gives us a similar looking estimate or what is different about that. Will you have to wait for, is the R Markdown file closed in homework? Is it not viewable for you?
When I go try to download the R Markdown file from the homework assignment, it opens a new page and it says the file is currently locked.
Well, let's see why that's happening.
I thought it was maybe just because we had to review more material, but
let's see.
Sure.
Yeah, that shouldn't be the case. Let me R Markdown. Oh yeah, that is not visible. Now it is. Okay. Let me make sure it's like the right file. Yeah, let me, yeah, it should be viewable, but I'm gonna just double check after class, make sure it's the most up-to-date one. Yeah. No, you don't have to wait for that. So you can definitely get started on a bunch of these. I'll post an announcement to just indicate like, hey, you should be fine doing some of these, and these are problems you might want to wait until after Monday to do.
Okay, great, thank you.
Yep. Okay, so if you have any questions, feel free to hang around. If you've got a few minutes, Stephanie, and you want to take a look at what was going on in your R file, you can definitely do that. Otherwise, have a nice weekend, everybody, and I'll see you on Monday. If you have questions, I do have office hours tomorrow, 10:30 to 11:30 as well.